Hello.
Can you
Hello,
hear
everyone.
me? Do people over Zoom can hear us?
Can you hear us?
Yes, we can hear you.
Okay, sounds
Very
great.
good.
Okay, let's get it started.
Now we cannot hear.
The mic got muted again.
Can you hear me now?
Yes.
Okay. So, yeah, welcome to the next Safari Live seminar. Today is my great pleasure to introduce you Prof. Yiran Chen. Prof. Yiran Chen received his BS and master degree from Tsinghua University and PhD from Purdue in 2005. After 5 years in the industry, Prof. Chen joined University of Pittsburgh as an assistant professor. And now he's actually a professor in Duke University. Prof. Chen has been contributing to the community by publishing many outstanding papers and also books and a lot of interesting patents. So yeah, Yiran, feel free to start whenever you're.
Thank you so much for keeping the intro short. Hello, everyone. I'll be very honored to be here to present today. But just to let you know, the reason I need to stay here because we couldn't figure out how to use the camera on the back. So I can only use the camera from my computer. So if I don't stay here, you're not going to see me. Okay, sorry. It's not because I don't want to stand up and talk. Just for your information. Yeah, but other than that, feel free to interrupt me if I'm talking about this. So the title of my talk today is Hardware Software Co-Design for Edge AI Systems. So when I asked my student to prepare these slides for me, I talked to them whether we should just present our latest work or give people a more holistic view about what we have done. We decided to go for second one because it's the first time for me to come to ETH, have a sit, and give this talk. And also, I believe this talk is jointly sponsored by the CAS, Computer Society, IEEE Circuit and System Society, the CAS, in Zurich. Okay, so you're probably going to familiar with this hardware platform for the deep neural network. I believe you're very familiar with the GPUs, how we're going to train the deep neural network on the backend GPU clusters. You may even heard about the large language model, ChatGPT or something first. People need to have more than 10,000 GPU to run to train the models, right? So this be generating a lot of power consumptions. And also you can use the IPGA because in some particular applications, the IPGA give us the very configurability, which would be more efficient, in customizing some operations. And also, if we have the large volumes of some particular task, you will consider use ASIC design, which can be very fast, energy efficient, but you will take very long development cycles. And also you have some novel architecture and emerging devices, as we discussed this morning and also afternoon with some students about the non-volatile memory or some other computing paradigm like a processing memories on the first. If you look at the whole AI system, it's going to be very interdisciplinary and also holistic research field. Not just have computer architecture and also the software solution stack. We can also have software hardware co-design, and many of you are working on, and also the circuit design, which we can develop the new circuit, especially the accelerators and to accelerate the computation of those AI applications, and also some innovation on the devices, even materials, to represent some behavior that can to benefit to the computation of the AI applications. So that's going to include the scale from the device to the array to the engine, especially to the accelerations, to the cores, including both the processing engine and also the memory, and finally the system. They can offer the large range of the computing power to be from a couple gigatops to even the 100 teraflop. So, in particular, the software group, one of the famous research is processing in memory. So in back to years 2005, even earlier, the Professor Arnold Mutlu's group, published paper regarding the DRAM-based near memory processing system. So this one we show here. Talk about how we are able to integrate the logic and also some other computing component into the DRAM process and to generate some benefit, kind of accelerate the different applications, not just the AI, but it could be some others. And the reason we can do this because if we consider the power consumption in the chip design, many powers are consumed by the data movement between the memory and also the computing unit. That being said, if we can somehow move those storage to the on-chip and also to compute, the computations within the memory modules, we can save, the data movement power. We can also implement this in some other memory technologies, such as SRAM, which give us, the more benefit in terms of the flexibility in the conventional CMOS design. That's one example I'm giving here is, we later on, we'll talk about this. Okay, so let's talk about the compute in memory circuit design. So I won't talk about the architectural design because I don't think I can do a better job than this group can do. So I try not doing this. Rather than give some ideas about what we have done in terms of the circuit design. So if you look at the percent in memory accelerator design, there are a couple of challenges here. So first challenge is large compute circuit areas, particularly in the ADDA conversions. Many design tell you we are able to compute this computation using the analog form, which we need to convert the signal from digital to analog and compute, and then convert the result from analog to digital. Such conversions will consume a lot of power, but also require the very large areas, of the ADDA conversions. If we can somehow get rid of this, for example, we can have a purely digital implementation of the near memory or the in-memory solution, we can actually dramatically remove this component. But they're going to introduce some other disadvantage, such as the higher power consumption or so on first. The second one is the limited, computing in-memory functions, because whenever we want to introduce new functions, we need to introduce a new logic in the memory cell. That is associated with cost in terms of the areas and in terms of the power consumptions. The third one is the deployment of the different variations of the algorithm to this processing or computing in-memory modules. Because now we have a lot of variations of the DNN models, and this will give us very different computations of the data, and not many of them can be really directly mapped down to the MAC design, which is a multiplication between vector and the matrix. We'll talk about this one later on. So last year in ISSCC, some of my students, they work with some other companies to propose something we call the dynamic logic-based ADC list, the SRAM theme. The basic idea is we're not going to use the ADDA converter versions. Instead, we have the dynamic logic to process the output from the CAM cores. And the advantage is we can certainly save the area and also save the power, and we achieve the highest power efficiency for the lossless, SRAM design in that year. But what we pay is we need to handle the very shallow, the bit line of the SRAM because we have a limited resolution we are able to handle by using this dynamic logic. So that's the trade-off we pay for it. Okay. So we take about a chip, we show our result in this 28 nanometer technologies. We show that compared with the analog SIM or the digital SIM, our result gives, pretty good, computing efficiency with reasonably good, the weight of density and so on first. And you can also find out the highest energy efficiency will happen when we apply the voltage around 0.8 volt, because we all understand, the performance of the CMOS device, will be improved if we increase the voltage, but we pay is the power consumption. So that's why you start to see even we have the best efficiency around 0.8 volt, but keep increasing the voltage to be higher level does not really give us better performance, because we start to paying something else as a penalty. So that's something we learn, from this. But of course, you can use one, as a processing element in their design, and we're still working on to scale this design to the larger, implementation with, the more diverse the interface that can be integrated this design to the different SoCs. Okay, so we have this design, and we also talk about, there is the array of this memory cell, which can be used to map, the DNA operation to this pin design or the SIM design. The next question is the DNA model suitable for this, multiplications, operations? The answer is no. If you look at, what people have done in the past couple of years, one popular topic is called sparsity. I believe, someone has been talking about this. Back to 2016, so when people start to optimize the deep neural network, the one simple intuition is this. If we have one parameters of the neural network, the value of which is small, very small, then any input times by a value close to 0 will be 0. So we can safely remove this width or these parameters in the computation with or with very minimal or even without the impact on the output. This is what we call the network pruning. Okay. The issue is, even we are able to remove more than 95% of the width because they are very close to 0 with very minimal impact on the accuracy of the model. If we really send this prune neural network, to the GPU to run, you actually cannot, really always improve the computational time. You actually, in many cases, even make the computation slower. At that time, the people cannot solve this problem, so they have two solutions. One solution is they came up with some hardware design saying, oh, I can handle this, the prune neural network, because I realize this because, this prune neural network, break down, the cache locality in the GPU. So we need to handle this, the random cache misses. Another kind of people that even just totally ignore this. They say, oh, I give you the theoretical improvement, which means I remove 95% of the weights and also the flops. I don't show the real computational time on the GPU. Neither of them are going to work. When we look at this result, we say, if we understand this as the cache misses we introduce, maybe the simplest way for us is actually trying to prune the neural network while still preserving the data locality. That should be the way to do it. This is actually the very natural thinking of our computer engineering people are going to do. We call this solution as a structural sparsity. That was published in Europe in 2016, I believe, or 17. So what we did is very simple. We actually apply something we call group lasso, which we group different widths in the structural way. And we actually prune the whole block, either whole column, the whole rows, also on the first, to still preserve, the rest of preserves, the width in the structural way. So we don't really sacrifice the cache locality that much. How we can do this? You actually can group, the width corresponding to the different filters, different channels, or different, filter shape, or even different layers, because they are organized as a block, or the columns, or the rows in the memory, which is prune this. And we also can apply this technique on this LSTM or the RM models like we use in the CNN. And we actually work with Intel to deliver their first NLP microprocessor, and you use our pruning technique. Now the structural pruning has been the standard process for the application of all the deep neural network. It has been supported by almost, if not, perform all the DN tools. So this paper has been cited more than 2,000, I think the 23 or 2,400 times. So we actually can do a lot of more stuff, to improve the performance. For example, in 2020, we actually can introduce, what we call the Hoyer square regulator to give the different widths on the different weights on the different parameters of the neural network to make sure we're going to preserve the large width and actually get rid of the smaller weights. So hypothesis here is the larger width, will generate, more sensitive output that going to impact the performance of the neural network. Okay, I'm not going through the details because there are some mathematical proof to show this, but this would be the one way to say if you can apply such an equation in the regulators, you're able to preserve this. We can do even more than that. Because people do the quantization, right? Quantization, you can have a 4-bit, 8-bit, or so on first. We actually combine the pruning with the quantization together. We say, if we know how we're going to do the pruning and the quantization, one way we should do is we introduce some structural quantization in the bit storage. For example, we may have the 4 bits. Originally, you can only shrink them down to the 3-bit, 2 bits by truncate the first bit or the last bit or first 2 bit or last 2 bits. But now what we could do is we can remove the bit in the middle. We say we will completely remove the columns, the second columns of all these bits stored in the memory by quantizing the data and represent the data using the rest of the 3 columns of the 4 bits. We call this a pruning, the structural pruning doing this. And this actually gave us the more flexibility in the pruning as well as the quantization together. And we are able to achieve the very high quantization rate while still preserving the very good results in this particular design. There's another example to show if you know how the data is stored in the memory, you are able to do the quantization in the structural way. We can even do more than that, because if we really think about the kernels we're going to store in our computing process, we have a very limited variations of the kernels that are going to be used to multiply with all the inputs. So one way we do it is we may have some basis of all the variation of the kernels, and we can restore those or represent or approximate those kernels by a linear combination of all these orthogonal bases, times by the coefficient. It's very similar as what we have done like ISVD or PCA, the decomposition. And we only need to store the very limited number of the orthogonal bases plus the coefficients that represent the different kernel weights. And by doing so, we actually can approximate the result by each time restoring all the weights using the basis and the coefficients, and to save the memory footprint and also the computational cost. There's actually another paper published in ICM 2020 by leveraging our knowledge about the approximation of the kernels to save the memory footprint and also computational cost. So all of this example just gave you some ideas saying if we have the better understanding about the neural network and how the neural network are computed in our computing platform, that we may be able to do some optimization at algorithm level, but to generate, the benefit at the hardware level in terms of the computational cost and also the efficiency. But that's not that's not the complete, story, because back to many years ago, we already started to design the architecture to support all this new neural network computation. There is one example we published in 2015 that talk about the RRAM-based accelerators. By the way, I think everybody here know about the emerging memory, RRAM, phase change, spintronics software. I'm not going to rephrase them again. So the basic idea is you have a lot of crossbar of those emerging memory. And this emerging memory cells resistance will be used to represent different ways of the neural network. If you have the current injected in this array, and you will be able to collect, the values, basically the voltage applied to this array. You will collect, the sum of the current, flowing through the columns. That will represent the sum of the product between all the input and also the width represented by some emerging devices. It's basically to compute the matrix of vector multiplications. And if you have many such arrays, the natural question you're going to ask yourself is how we are able to organize those memory register or the RRAM arrays or the emerging memory arrays to map, the larger deep neural network to the smaller crossbar, and also to guide the data flow from one layer to another layer, right? You may need the network on chip to handle this. So in 2015, we analyzed an architecture saying you have a lot of memory register crossbar array. They're connected with the neural network on chip, and they can guide the data from one to another one, so they can basically map the large neural network, down to the smaller crossbar arrays, while still be able to guide, the computation from the layer to layer. We have our internal compiler to identify the portion we need to accelerate, of this neural network, benchmark, and also to do the simulation to show we have a tens or 100 times performance improvement. That was one of the earliest work for us from architecture level to use for the solution. But now you think it'd be a very simple solution, right? But back to 8 or 9 years ago, and at that time, people haven't really even thought about what will be the architectural support from those things. But you immediately realize, if you have a larger number of this processing element, when we are mapping the deep neural network, could be, for example, different layers or so on first, down to this processing element, we need to somehow schedule them in the proper way so that we are able to maximize the use of the data flow from one layer to another layer, and from basically one P to another P. In general, there are two ways we can parallelize, the computation of the neural network. The first one is layer-wise. We have different layers, and they are able to compute simultaneously, and they're able to partition to the different P's. Another one is the data part of them. Basically, we just supply the different data to the same copies, and we run it, and we will later going to combine them. Now the question becomes, if we're really trying to map the deep neural network, down to this P, so which part of them shall we use to partition the workload? And apparently, there should be the combination of both, and there's no way for us to say for one layer and all the corresponding PE will be partitioned only for one type of the part of them, because we can do both. So the 2019 HPC paper basically the hyper saying we can exhaustively search, the optimization between the trade-off of two partisan on every single PE to make sure we're able to map them down to the format which actually maximizes the data flow bandwidth of this design. So this basically chart showing we have black and white, each color represented the data partisan or the model partisan. Even for the PE corresponding to the same layers, many of them will be conditioned to the data partisan, but some of them will apply to the model partisan. That's the work we have done to achieve the highest performance. 2020, we realized we're actually missing one thing, which is another partisan, or the tensor partisan, or the tensor partition. Because when we are computing the convolutional neural networks on the first, so in many cases, we just compute the intermediate result. Later on, we add them together. This is actually another partisan which we can implement. So if I have three types of the partisan, we basically have a 3 times 3 equal to 9 different combinations, between the two adjacent PE partitioning. So we actually have the different optimization on this, and then we create the layer-wise partitioning, to partition the different PEs to the different types of the partisan, and we have the hierarchical and recursive, the partition that we show in the left bottom one to show we can have a very high level partition. Later on, we can shrink them down to the smaller granularity, then eventually control the individual PE partition. And we have 3 different colors. We show even for one layer, so we have 3 types of the partisan we're going to apply to the different PEs. And so on first to achieve the highest performance. They're called the ACK part. Okay. So this actually the mem raster based or this the PE based optimization can be applied to many advanced operations. For example, we can use this one to apply for the generative adversarial network. They basically have the 2 parts. One is the generators and one is the discriminators. They talk to each other to basically generate some samples which are not be able to implicitly recognized by the discriminators. Either going to synthesize one or going to be just the real one. And by doing so, we are able to generate the samples which looks very real. That's actually be the foundation of the generative AI. And we analyze the whole pipeline to find out there are huge overlaps in this pipeline. If we have 2 passes, one is for the real sample or the synthesized samples, we're able to dramatically reduce the computation cost if we can intelligently leverage these overlaps. So that's one example we did. Another example is back to 2019. We say we actually can handle some operations, in the generative network, like a transpose convolution, which requires the zero insertion into it, to make the receptive field of this neural network larger and larger. So rather than we actually insert, the 0 first, and then to compute, which generate a lot of unnecessary computation because 0 times anything will be 0. We actually going to compute first, and then we inject pretend we actually compute this 0 times something, and inject those zeros into the final result to generate the larger one. Those are the small tricks we play, for the different applications, this deep neural network stuff. And this afternoon, some people talk about transformers or the attention models, which is very unfriendly to the mem raster array, which whose the writing operation is very costly. Unfortunately, the attention model needs to generate some intermediate result, which needs to be right into the mem raster crossbar again. So we have one paper in 2020 talk about we are able to push this computation to be very, very end, so that we only need to compute once and write them once rather than we actually write them twice. So to actually save the energy, to input the endurance, even not that much, maybe double, but it's good to have it. And some people talk about the softmax can be very costly, and we come up with RM-based compare and select in the block, which can compute the softmax iteratively to save the power. you probably know, this RN stuff actually can be applied for the graph computing, right? Because really nothing different, between the Mac design and also this graph computing, like, the first, like the depth first in the search or the breadth first search. It's just about if we're going to compute all the rows simultaneously or just one by one. So we actually apply the members the crossbar array to this graph-based computing engine we call the graph R, and receive 100 times performance improvement compared with the conventional design. So that's the one work we have done. And later on, work with Vijay, from Penn State, working on this graph in situ sparse graph analytic accelerator, the GAS-X. The basic idea is, at the end, there are many matrices in the graph computing are full of zeros. So we actually, instead of map the whole matrix to this members crossbar array, we just have this link tables to represent all these non-zero elements that can only use this link table to compute whenever it needs to compute, to save the performance, to save the energy cost and the computational cost. This can further boost the performance by 7 times compared with the graph R. Okay, there are many latest work. I just stop here. It's just for me, there's small tricks of all this sparse neural network. For example, we try to explore the reuse of the data, which actually can push the pruning of the neural network to be very, very earlier. And we're not going to allow the data to be reused later on, so that we actually totally remove the data reloading operation if the data has been used before to improve the performance. But those are some small tricks here. Published on last year ESCOS or something first. So that's about distributed learning. In many cases, you won't limit the training of the neural network to only one individual computers or servers. It's actually very true, for the large language model, which requires thousands of GPUs. Now the question becomes, if you have so many nodes or clumps, training only one models, how you can partition them? How you're able to aggregate this computation in somewhere, so I'll be able to consider the contribution from all these distributed clumps. So one example is the parameter servers. The basic idea is very simple. You have a lot of workers or the clumps, and each of them have the full copy of the neural network you can train, but they all face different training data. So if you start to train the neural network, the models, it will generate the gradients based on the data you're facing. You generate those gradients, but you're not going to use the gradient to train the model directly, because this can only give you the bias of the data you are facing. What I really want is actually contribution from all over, the world workers in the system. So what I can do is we allow this worker to send the gradients to the central servers and do the aggregation, and then send the aggregated gradients back to every single clumps. You will immediately realize it's not going to be very scalable, right? Because if you are increasing the number of the workers, you need to do 2 ways. One way is you need to have a larger and larger bandwidth between these workers and also the servers to do the aggregation and make sure the server will be fast enough. Or you actually have a hierarchical structure so that they have created multiple layers, and each layer only going to do the aggregation for the clumps controlled by this layer, but you will start to lose the accuracy. When we look at this, we say, look, if we are able to transfer the large number of the gradients, then why we really want to transfer the raw value of the gradients? Because the gradient itself will become the statistical. We maybe just need to transfer the mean and the variability of the gradients, and also restore, the whole gradients at the parameter server. That's what we propose, called the tangram. And by doing so, we actually also can quantify the gradients from the floating point to 3 levels, 0, -1, and +1. so that we are able to restore the distribution of the whole gradients transfer between the parent server and the workers. And this work, has been studied more than 700 times and implemented on the HP product and later on in many products of other companies. And we apply this one to the mobile system because they are more sensitive on the utilization of the bandwidth between different workers. And then later on to the testing, you are able to just do the testing on each device, but you can do a little bit more than that, because for the convolutional layers, that's going to be the computing intensive, but for the contact layers, it'll be the memory intensive. Memory intensive means that there are a lot of weights, and computing intensive means there are a lot of reuse of the weight. So what you're going to do is you're actually going to find out the sparse models and cluster those models to the smaller region and to map this very dense region down to the each cell phones. By doing so, you try to minimize the communication between different cell phones, but that'd be very costly. Especially you need to create, the handshake protocol between different, devices and also to perform it. So you're not going to do this. So that's why this actually received the Best Pair Award in the day 2017. You mentioned you were there, so yeah, in 2017 date. We actually, some students, they say we can do something else. For example, we can do the decentralized deep learning. We don't have these clusters or the servers to send to, because this still creates some security concern. Rather to do the decentralized deep learning, so any device will own more than 50% of the gradients or the weights, or the gradients. And by doing so, if we really want to do something bad on this training process, you have to control more than half of the services running on this training. That's actually a paper we published on the IBM Cloud computing. And we actually did work with some companies to deploy our distributed training testing stuff on the 1,000 servers globally, and to try something we call the mobile video style transfer. It's something like, you have the screen here. When you take a photo, you will automatically transfer this image, this photo you took, to the winter style. For the same. So, but this actually require very computational intensive operation, which where you offload to some centralized servers. Actually, also need to coordinate this operation between different clients. We deploy this to the international. It's actually a paper published on Mobile 2020. Okay, so you start to see we gradually move up our stuff, to a higher level, and then we do the security stuff. Because at that time, we say if we really want to transfer this information from the workers to the servers, I still worry about the privacy of the data. Right? Even we send the feature, we don't really send the raw data. I still worry about this. But you also need to realize if we send the data to the servers, if we don't send anything, we're not able to perform our task. So there's a trade-off between the information privacy and also the data utility when we transfer the data between the client and also the server. So we come up with something we call the privacy preserving data crowdsourcing framework. It's basically federated learning, saying if we want to send data back to the servers, we need to basically to optimize the two objectives. One is to maximize, the possibilities to retain the original information, but to minimize, the data privacy leakage. And by doing so, we're able to make the trade-off be between them, which quantified the guarantee. This paper actually received the best student paper award from the KDD, which is the data mining and the knowledge representation conference. we're the computer engineers, right? So we always want to improve the efficiency and the heterogeneities, so on first. So we say if we really want to transfer the network from the local server, local clients to the servers, we probably don't really want to transfer every single width or the corresponding ingredients. It would be very costly. Can we do simpler than that? So one way we did, say we actually come up with something called the lottery federated learning. We actually have very large, the neural network, and we just have the sub network, which is a subset of the neural network, to transfer from each client to the server and do the aggregation. The reason we have a subset, including two advantages. The first one is we don't need to send the whole network to the server, which reduces the traffic. And number two, because on each client, the subset will be different. That's basically called the personalization, that we're going to train the local client to customize, the performance for the data they are facing locally. So that's called, the lottery federated learning. But in another paper we published also in 2021 in the census, we say we can do more than that. We don't even transfer the subset of the neural network. We just transfer the mask, which is just 0 and 1, to allow some width of the neural network to pass this mask to transfer. For any others, we just a block. We don't need to transfer. In other words, we don't really transfer any width. We just transfer the mask and do the aggregation and transfer back to the clients. But because we have a larger number of the elements of the mask, we can train the mask to really do the personalization of the training of the neural network and to make sure they can be they can be performing very well on the data in the local. But by doing so, we have a much more efficient, the data transferring and also the very low computational cost. I want some other work like the security of the federated learning or something. I'm not going to all the details. I think that's maybe a little bit far from the interest here, but that's published on the CVPR and the NeurIPS, which you can read. So for this model invasion attack, also for the model poisoning attack. So a lot of people working on the hardware software co-design. We try to design the neural network where it can run efficiently on some powers. In the past, we have to manually optimize this neural network, but it's not going to be the scalable approach, right? Because we have a larger models and more features we need to optimize. We have a better and more understanding of the data. But all this will rely on the personal experience of the designers. I think the bad idea. And we automate the whole design, which we call the auto ML. One subfield which is very popular is the nuts of the neural architecture search. The basic idea is very simple. If we can exhaustively search to optimize the solution for the neural network, which give us the best performance with some budget, or we just achieve the some performance requirement with a smaller hardware cost. But that can be the exhaustive search. So it basically costs the thousands GPU hours to just search for the neural network. Can we do better than this? 2020, we say we can represent all the neural network as the directed acyclic graph, because it's just neural network is really nothing else but the graph. And we have a partition neural network to be the cell, which is the smallest module which we can optimize at the architectural level. And within the cell, we have a few edges to connect the different operations. We can randomly remove some edge and make sure we have a smaller cells, but we can see how the removal of this operation will impact the performance, and we keep this optimization towards some directions, which actually gave us the best result. This we actually call the topology-aware search. We actually can convert the neural architecture search to be the optimization problem of the topology of the neural network. And we can even design some predictors. It's also the training of the neural network. to convert the encoded topology of the neural network, map them down to the prediction of the accuracy. If it gives the neural network, as I can make the prediction saying this neural network pretty much give us the better or worse performance, and then we use this result as the guidance, to really guide the optimization of the neural architecture search. So why we want to talk about this? Because this is basically the optimization process. It's not just only the performance or the accuracy of the neural network can be used as the goal in this optimization. There can be other constraints like power, as one example. Some people ask me about if you have a neural network, the software, how we can estimate the power consumption. You can profile this neural network on the different hardware platforms and use this one as the parameters sending into this loss function of this optimization process and also optimize this. And they can also have some other parameters like latency. That's another one. And also the memory usage is another one. You can apply all these constraints in this optimization and give you the best result under the requirement of the performance or the accuracy of the neural network. There's another example saying you actually can do the predictor-based approach in the DAG, but you can convert all these topologies to some encoded, the dimensions, and the similarity between different topologies will be represented at the angles between the different vectors. Each vector will represent each topologies of the neural network. And by doing so, you can have a very high correlation, as we show here on the right, bottom one, to show the correlation between our encoding scheme and also the performance. And we just need to calculate the similarity between the different topologies. We can predict very accurately about the performance and of the neural network to give us the guidance to optimize this neural network, no matter what, performance, power consumption, latency, so on and so forth. If you really think about this, it's not the way we usually design, right? Because if a human really design a neural network, you don't design like this. You don't have a lot of operations. You just randomly stack them to see how we're going to optimize this. You always start something very small to see if the small neural network going to give us a good performance to meet our requirement. If not, you add more layers, more complicated operations, or you start to grow the neural network from the scratch. This is something we call the auto grow. This is a methodology we're proposing in 2020 in KDD. We start with a minimal neural network to check if the neural network is going to meet our requirement. If not, we add the more layers, and repeating the more modules and to see if we can able to meet this requirement. We need to design some rules because we cannot just randomly explore the structure. We design, how we're able to what is the criteria for us to add the more layers within the cell? What is the criteria for us to add more cells, repeat them, so on first? And what we found that is we can always, reach out the Pareto surface of this trade-off between the performance or the accuracy and also the computational cost, as we show here. But we have no control about the trade-off. In other words, it's really hard for us to control. We want the precise trade-off between we want this accuracy and this minimal computational cost. We still don't know the answer yet. Looks like we still need another types of the constraints to guide this auto growth solution. So we stopped there. So it was published in 2020 KDD. The last one I'm going to talk about is actually a little bit far from what you're working on, but more relevant to the hardware design. We can use the machine learning or the AI model to automate the electronic design automation, which can help us to design the chips. This is one example we published in the 2021 micro. The basic idea is we want to estimate the power consumption on the chip in the real time. You have a lot of switching activities, right? And you are able to approximate, the power consumption of the whole chip if you have all these informations. But the issue is, we are able to estimate this power consumption using these switching activities. This computation must be simple enough so that we can really compute those things. We use minimal hardware that can compute the results in the real time, give us the millisecond accuracy. This paper basically showed that we can have some proxy of the RTL signal, which is the highly optimized features of the neural network to represent, the power consumption of the chip using the highly selected samples of the switching activity on the chip. I'm not going through all the details. The result basically show that the green and the orange, as a button, show that we can offer very fine granularity estimation with a very high accuracy on the chip using very simple, only 10,000 gate to approximate this. And this actual technology has been used in the latest ARM course. And this paper actually is surprising to me, received the best paper award in the Micro 2021. If I'm not consider myself as a diehard architecture, I don't know why they love this paper so much, they give me the awards, but I take it. Yeah, but this actually show, how the machine learning technology and also the EDA technology can benefit, the microarchitecture design. You can also use one, for some other solution, like routability of the chip design or the analog layout optimization. I'm not going through all the details, but it's a very simple application regarding the neural architecture search, for this design. But one thing I want to mention here is we are not the first one using machine learning for this EDA problem, but we're maybe the first one using neural architecture search doing this. But after we publish a paper like this, nobody continue doing this because you cannot bet what computer search. So they say it's done. Okay, we're working on something else. With the computer jump into it, if we really don't care about how much computing resources you're going to use, computer will always do better job than human can do to find the best solution, obviously. So yeah, we can do some security, machine learning platform for the EDA. We allow the multiple people to contribute their data in a distributed way, but we can preserve the features, the privacy on the first. I'm not going through the details, but also what we have done. And actually, this paper, the recent paper, actually received the best award in the SPDAC 2023. Really this year. Yeah. Okay, this is my roadmap. This basically show we start with a very simple one, which I did not even show. We start with a very simple device. So we use the memory research design, the synapse, the neurons, and then the array, then the circuit. Then we started building the processing element, the architecture, software stack. We started being algorithm optimization, distributed learning, federated learning, privacy, so on and so forth. So you start to see we actually start with very low level, but gradually reach out higher and higher level of doing this. That's actually how we're doing research on this. Currently, we actually have all this kind of research in my group, working on very interesting and also the interdisciplinary research about this. To make the concurrent, so the non-conventional hardware architecture of being critical for the AI applications, you'll see there's so many variabilities there. And the co-design workflow can further push the frontier of the system performance and efficiency, but you may want to have a better understanding about how the both sides, how they're going to work, and to work together. In many cases, you want to talk to your colleagues about this, and so you want to automate the co-design flow, which can be very necessary component in the future AI system design. Because if we really tell the machine what are the rules, what are the experiences, even you just fit in with the old design and old trade-offs or the rules or policies on first, the machine can do much better than we do to exploring all the possibilities. That should become very exciting. So now you start to see, the ChatGPT like tool, they start to programming, optimize the algorithm for themselves, right? That's how they can involve themselves. That'd be very, very exciting the next decade. So these are some references. I'm open for any question you may have. Yes, thank you.
Thanks a lot, Yiran, for the excellent presentation. We have some time to questions. And this is a microphone I'm gonna distribute, hopefully.
Hi, Professor. Thanks for the talk. So I have a question about the work on the monitoring the power consumption. So when you're doing, probably this can enable other optimizations, right? So based on your power consumption, you will decide what to switch out and or how to basically turn off some components in the system to gain more. Like, what is the optimization that you're shooting for when you can monitor the power consumption? Let's say that I do it on the fly really accurately, that's fine. And this enables it, right? But then what's the next step after that?
Yeah, very good question. This will be one of our earliest work about the power prediction, the power, estimation on this, right? I mentioned it. So if you look at the philosophy here is very simple. If we're able to collect all these switching activities, don't care about how many we have, we can simply calculate the power consumption by adding them together. Of course, physically, it's not possible because there's so many, right? So we can simulate all those inputs, the many inputs, like the 10,000 inputs, but not all of them are equally important. So you're able to identify maybe 300 most important features and get rid of any others. That's the first step we can do. And then you can train the neural network, to do the feature engineering to retrain the neural network, so that the neural network can adapt to some form which can more efficiently to extract the information carried by this input features. That's another way you can reduce, the overhead. So eventually, for the multiple iterations, you will make the trade-off between the accuracy and the number of the traits you will preserve. So you have a very low, very lightweight, the model and also the input. That's what we have done. But in the future, you want to make this flow more generic. So that's what my student, they are doing now is they actually generate the risk-fied design. And on the other design, they give you automated flow. So if you give them the design, they will automatically generate this power estimators design. You just implement on the chip. You don't even know what's happening in this flow. Because you don't worry about the model optimization, you don't worry about the feature engineering, you don't worry about, I will say the iterative optimization on the first, and or don't worry even worry about the technology or the manufacturing process, this also contribute to this stuff. So and they also want to try to integrate, for example, the optimization in the Verilog code or the high-level synthesis. So they're able to optimize, their design to better represent the power consumption in this, the topologies. So there are many things you need to do to automate the whole, we call the power aware, the chip design. Yeah. Yeah.
So I think I have also one question. So regarding that topic, to use ML for computer-aided design. So one of the challenges in designing chips is floor planning of the components. So are we also considering using that ML for better floor planning, and also for FPGA, considering place and route, for example? There are many heuristics that people are taking for that phases. So can we also use ML for that?
Yeah, there are many works actually in the floor planning, the routing, high-level synthesis, the fine-tuning of the hyperparameters in the synthesis, layout. There are many. I mean, I will say machine learning is particularly useful in the implementation phases, which means no guarantee, just statistically better than any others. There are another types of EDA tool called the sign-off. Basically, it means it's assurance. I just guarantee that you're going to work. It's less attractive because machine learning is basically the statistical model. It's no guarantee, at least no assurance on this one. There's less attractive, except for the verification, because, you know, again, this be like a coverage of the stuff, you know, there's no guarantee again, right? So otherwise, that'd be tough, yeah. But it's very popular research topic in the EDA, yeah.
Okay, so one more question. So regarding processing memory, given the fact that basically ML workloads, the data set is getting larger and larger, do you think there can be in the future the killer application for processing memory so that, I mean, people invent more?
Yeah, it's a very good question. Believe it or not, actually, the bottleneck is not really processing in memory. Bottleneck is actually the interface. Think about this. You have it's our array. How large you can make? 128 or by 128, 256, maybe pretty much the one, right? If you need a larger one, you need to parallel them. So we are able to make every single array functioning simultaneously. It's very hard for us to fit the data like this, because if we want to fit so many data at once, you know, sent to all these arrays, you know, the bandwidth can be very large. And what are the highest bandwidth we can give on the chip? It could be very limited. So I think the issue is the pin itself can be very efficient, but the bottleneck becomes how we're able to fit, you know, our data in a timely manner into this pin cores. We need a more, actually that should be what you guys are good at, right? To come up with a new memory interface or Cocke to support this, especially in the parallel, you know, setup of the pin. Yeah, I mean, people certainly talk about, you know, high bandwidth memory, but still HBPMs, but I still feel like this is not sufficient. Yeah.
Yeah, I mean, that makes sense.
Yeah.
That's actually one of the main problems with, I guess, accelerators. I mean, data should be fit to the accelerator.
Accelerator is a little bit different. If you look at all the accelerators, they either have a relatively smaller array. They have a distributed, you know, the cache. You know, they have a, I don't know, 32 by 32. They have a large cache around it. They have another one, but also another cache around it. Oh, they have a cyclic array. They have larger data reuse in between. Whenever fitting one type of data, you don't worry about this. So, but pin is different. Pin just like you send all the data to the computer at once. That gets data. It's very efficient, but which means if you'll not be able to fit the data in the same pace, the pin will not be unleashed, you know, or maximize its advantage.
Yeah,
I think that's the issue. Yeah.
Okay. Any other questions? Also from the Zoom audience.
So what is the typical time taking for NAS, your architecture search for a certain application?
Prithvi, could you please repeat your question? We couldn't hear you well.
So what is the typical time taken for neural architecture search for a certain application? You can give an example.
What's the average time for the neural architecture search? It really depends on what technology you use. It used to be, you know, the Dart or something that could be very long because they use reinforcement learning based search. Later on, people use the differential optimization, be much more efficient, but less accurate. There's always a trade-off basically in between. Now people trying to, and also the trade-off between the training and also the inference, right? So there's some that they like, you know, the one for all. They just train the neural network supernice just once, take a very long time. But after that, you know, when you really optimize the real problem, you just pick, you know, the subset of this supernice, you just run on it. they're all different trade-offs, which you can make between the training time, the inference time, the optimization, or so on and first. Yeah, there could be a couple thousand hours to just like a few hours. Yeah.
How do you come up with the reinforcement learning technique for a certain application? Means what is the key idea behind it?
Oh, I mentioned it, reinforcement learning is basically use reinforcement learning for the optimization of the knots. That's what I mean. Yeah.
All right.
And also some people use reinforcement learning for the optimization for EDA. Yeah, but basically it's just like another type of optimization process. Yeah.
Thank you.
Yeah.
Any other questions? Okay, let's thank the presenter again
Yeah, thank you.
for the excellent talk. Okay, thanks everyone, and see you all in the next Safari live seminar. Bye.